This is the last part of titration curves, and this is about choosing an indicator. Okay, so the indicator should change color. This is the key thing, is that the indicator should change color at the pH of the equivalence point. Okay, so for a strong acid, strong base titration, the equivalence point is 7. And remember the pH is 7 because the salt does not hydrolyze. So for example, we could use bromethymol blue because bromethymol blue changes color from pH 6.0 to 7.6. That's really nice. Mhm. However, we often use phenolphthalein, even though phenolphthalein doesn't change color at pH of 7. It changes color at pH 8.2 to 10.0. But what I want you to notice about this is that phenolphthalein will change color at this pH, which corresponds to, I'm not doing a very good job of drawing my line, but it corresponds to a volume of approximately 25 milliliters, which is really close to the same volume as pH 7. Because we have such a steep part of the curve there, because it's essentially vertical that whole way, you will get phenolphthalein changing color at the same volume as bromethymol blue would change color. Okay? Now, if we were to go to something like methyl orange would change color just a little bit early. Okay? I know I've drawn that on a diagonal. All right, so you wouldn't actually get the same volume as the pH of 7. So methyl orange would not be the best choice. Okay, you could get an even worse choice. You could have, oh, let me grab my table here. You could choose, let's see, what if we were to choose methyl violet? Methyl violet changes pH. Methyl violet changes pH from 0.0 to 1.6. And you can see that 1.6 would be about here. Okay, so from 0 to 1.6. So it would really actually already have changed color before we even started our titration. So methyl violet would be a terrible choice. It would start, it changes from yellow to blue as we go from 0.0 to 1.6. And it would have changed into its blue form, its basic form, before we even start the titration. It would just stay blue. It would stay blue and blue and blue, and you could add volume till the cows came home, and it would just stay blue because it has already changed. So you need to pick something that's going to change color within the vertical portion of the curve. So you're looking at anything from here to here. Methyl orange might kind of be okay. It's a little bit dodgy, but it would sort of be at the end of what we could choose. Okay, let's see. Do-do-do-do-do-do. Okay, here's a question for you. Is methyl red, here's methyl red, a suitable indicator when you are titrating a strong acid with a strong base? Could we use methyl red? Absolutely we could, because it will change color at 50 milliliters, right? And our equivalence point, where does our equivalence point take place at? It takes place at 50 milliliters. So yes, methyl red would be fine. Phenolphthalein, would phenolphthalein be okay? Yeah, absolutely. Phenolphthalein will also be okay because it will also change color within that vertical section of the curve. Okay, there we go. Do do do. On the graphs below, let's mark the volume corresponding to the end point. Now let's just make sure we understand the difference. The end point is the pH, at which the indicator changes color. And remember, the equivalence point is the point where the neutralization is complete and there is no excess of either reactant. So let's take a look at our end point. Our end point for phenolphthalein is right in the middle of its color change. So the end point is here. So phenolphthalein would make a good indicator for this particular titration. By the way, taking a look at that curve, can you tell what kind of a substance is being titrated? What is in our flask? What kind of a substance would be in our flask? Or in the beaker in this case? In the beaker. Okay, so in our beaker, what we're starting with is it's definitely an acid, right? Because the pH is low. See that low pH? Is it a strong acid or is it a weak acid? Okay, when you're asked if it's a strong acid or a weak acid, I want you to take a look at some features of that curve. I want you to take a look, first of all, at this little bit here. Okay, right here, we have a hill. When we have that hill, that tells me that the acid is weak. Okay. The other thing I want to look at is I want to look at the equivalence point, right? If I look at my equivalence point, the pH is greater than 7. The pH looks to be about 9-ish, okay? If the pH is greater than 7 at the equivalence point, that means your acid is weak. Okay, so I want you to be looking out for those clues that you have a weak acid. If it was a strong acid, there would not be a hill at the beginning, and the pH at the equivalence point would be exactly 7. Okay. Why do we get that pH greater than 7 when we are reacting sodium hydroxide with a weak base, or sorry, with a weak acid? Let's call it HA. Why do we get a pH greater than 7 at the equivalence point when we have reacted all of the acid and all of the base, and these are all gone? Why is this solution have a pH greater than 7? Need a little review there? Ooh, ooh, yes, there is hydrolysis. Absolutely. Okay. You will always, as a result of neutralization, have water and a salt. Okay. And if you had a weak acid, you will also be producing a weak conjugate base. Okay. And you will have hydrolysis. So we would have A minus, which is a weak base. It would react with the water. And we would end up with HA plus OH minus. Okay, so the first thing that happens is that you have neutralization, right? This part here is the neutralization. At the equivalence point, all of that, those reactants, the strong acid and the weak, or sorry, the strong base and the weak acid are all gone. Once neutralization is complete, all you have left is the salt. The salt's going to contain an ion, and if you had a weak acid, you will have the conjugate weak base, and that weak base will hydrolyze. So that's going to be something for you to really, really stick in your head. This is a question that comes up all the time. Why is the pH greater than 7 at the equivalence point when we react a strong base with a weak acid? And most people, when we react a strong base with a weak acid, most people will say, oh, because the base is stronger. And that's not an answer at all. You need to talk about, why are you getting hydroxide ions? Okay, so when if you're asked, in fact, yeah, where am I going to put that? If asked why the pH is greater than 7 at the equivalence point, the answer is not because the strong base is stronger than the weak acid. The answer is hydrolysis. Okay, and hopefully the worksheet you do today will help you practice that and remember it, because it is one of those things that people always, I don't know why, they just forget it, right? It's one of those things. Okay, going back to our indicators, oh, and don't worry, I will print this off as a PDF and save it. You should also, I believe, be able to access our notebook through Teams. Okay, so this should, I think, be available for you in the notebook on Teams, but I'll print out a PDF as well just in case. Could we use methyl red as our indicator? Well, the answer is no, because methyl red is going to change color in the middle of its, I should do a different color, that doesn't show up. In the middle of its color change, we would have a volume of 32 milliliters. At 32 milliliters, we have not neutralized all the acid. We still have excess acid. So the end point at 32 milliliters does not equal the equivalence point, which is 50 milliliters. Alrighty. So you have to make sure that you choose an indicator that will actually change color where you want it to. And that is basically it for the unit. We are done unit 2. Not unit 2. We're done the unit, which is acid base part 2. So what does that mean? Well, it means I would still like to give you guys some sort of quiz on titration curves, titration calculations and titration curves. Remember, these are for participation marks. But I don't want to give it to you until after you've done the worksheet on titration curves and had a chance to ask some questions about it. So we'll look at that for next week. Okay. I'll have to look and figure out when we're going to do that next week. So strong acid, weak base. Okay, so in our burette, we would have our strong acid. For example, that's going to be HCl. In our flask, we would have our weak base, which, for example, could be NH3, ammonia. So our neutralization reaction will look like this. We will have HCl plus NH3, and I want you guys to try and predict what the products of that reaction are and whether we have a one-way arrow or a two-way arrow here. So predict the products and let me know if that's a one-way arrow or a two-way arrow. Yeah, because the HCl is strong, that is a one-way arrow. So hydrogen's, HCl is going to be like, okay, I'm just going to give away all my protons. Ammonia, I don't care if you want them or not, you're going to take them. So hydrogen gives its proton to ammonia, and we end up with Cl minus plus NH4 plus. Now, you could write it like this, or you could write it as the salt combined, which would be NH4Cl. Regardless, you have to look at that salt we have a salt produced. Does it hydrolyze? What do you guys think? Does it hydrolyze? Yes, absolutely it does. The NH4 is going to hydrolyze. So we have NH4 will react with the, yeah, you can go ahead and do that. Sorry, just talking to my son. It will react with the water, and we will get NH3 plus OH minus. Okay, and what that's going to mean is that at our equivalence point, the hydrolysis of the salt, produces hydroxide. And therefore the pH is going to be, is it going to be greater than 7 or less than 7? What did I just do? Oh my God. Isn't it supposed to produce hydronium? You are absolutely right. I goofed up there. Yep. Okay. So let's get rid of that. Sorry, I've got two things going on right now, and my brain doesn't do too well when I have two things happening. Liam, are you okay there? You got everything under control?
Yeah. Is it alright if I open a new tab to like do?
Yeah, that's fine. Yeah, go for it. Okay, so back to the drawing board. We have now produced H3O plus. So our pH will be greater than 7 or less than 7. Yeah, it's going to be less than 7 because that's acidic, okay? So we have less than 7. So for our strong acid, weak base, when we have our pH here, we have to remember in the flask is our base. So the initial pH is high. Okay, there's our high initial pH. Do you remember what happened at the beginning of the weak acid, strong base curve? What feature was there at the beginning of the weak acid, strong base? Yeah, absolutely. There was that little hill. And we're going to have a little hill too, but in this case, it's like a downward kind of hill. Okay? So again, we have a little hill. Okay? And then we have goes down sort of steady. And then it will, got to draw my vertical section actually looking kind of vertical. Drop. Okay. And the pH in the middle here, I've drawn this terribly. I think I'm going to move this up a little bit. There we go. That looks marginally better. The pH here at our equivalence point, if this is pH 7 here, that's going to be less. I've not done a good job drawing this. When I post the PDF, you'll have the nicer picture of this. So the pH is less than 7. And that is due to the what of the what? Why is our pH less than 7 at the equivalence point? Due to the hydrolysis of the NH4, yeah. So it is always going to be due, if the pH is not 7, it's always going to be due to hydrolysis. And that's going to be the hydrolysis of whatever salt you have. Okie smoky. So if we were to summarize our 4 curves, we would have one that looks like this. We would have one that looks like this. We would have one that looks like this. And one that looks like this. All right, and in each case we have our pH. There, and along the x-axis is the volume of titrant added. And that's the stuff in the burette. So, yeah, what are each of these curves? Let's call this top one curve A. What have we titrated with what? Yeah, this is titrated. We titrated a strong acid with a strong base. What do we have in curve B? Yeah, it is a weak acid. Whoops. With a strong base. And when I write it this way, you always want to remember that when we say a strong acid, that means that's what we're starting with in our flask. And when we titrate it, we're titrating it with a strong base. That means we're adding in the strong base. So that means this is in the flask and this is added in. The weak acid is in the flask and the strong base is added in. How about C? Yeah, that is a strong base with a strong acid. And lastly, we have a weak base with a strong acid, yes. Okay, and please do remember that you have your little hill for your weak titrations, okay? Your pH is going to be 7 at the equivalence point for your strong. The equivalence point is going to be greater than 7 for your weak acid with a strong base. And your pH is going to be less than 7 for your weak base with a strong acid. Just one other thing. Do you remember? I need another pen here. Where are we? Oh, come back. Let's do green. This area in here. Do we remember what that area is all about? What is it called? And why do we call it that? Anybody remember what that's called? That little green region there. It is a slope. It is the buffer region, yes. And it is called the buffer region because you still have half of, say, the weak acid left. So half of the weak acid is still left unreacted. And half of the weak acid has been turned into its conjugate base. So in other words, we have lots of weak acid because there's still half of it left. And we also have lots of the conjugate base. So this would be maybe HA, and this would be the A minus. Okay, and when you have lots of weak acid and lots of its conjugate base, that means you have a buffer. That is what a buffer is. Yeah, the halfway equivalence point. Yeah. How are we feeling about titration curves? Good, okay, good, good. All right. So I will send you off to do the titration curve worksheet. Do we remember that we have a meeting on Saturday at 9:30? This Saturday. We talked about that last week. If there is someone who cannot make it for whatever reason, it's not the end of the earth. Again, like always, the meeting will be recorded and I will post it. So if you're concerned about that at all, that's fine. Basically, all we'll be doing is going over questions that you have from the titration curve worksheet. So if there's any problems that you've had, that's when we can go over that. If you're having problems and you can't make that meeting and you'd like to ask, don't hesitate to send me a message, or we actually have flex time on Friday. So if you'd like to just book a one-on-one meeting, we can certainly do that as well. On Saturday, after we finish the titration worksheet, the homework after that is going to be the overall unit review. So I will actually post that up if anyone wants to get started on it. You will be able to get started on it, but that will be the homework on Saturday. Overall unit review, Saturday homework, today homework. This is not a small assignment, so I think we have a meeting. Is it the following Monday or Tuesday? Oh, it's Wednesday. Okay, so maybe we'll make it like I don't know, the multiple choice or something like that. Multiple choice. Okay, and we'll see where we get to from there. If you would like to have 2 sessions next week, then my suggestion would be that even though Monday is a Pro D, we have a meeting on Monday. If you don't want to have 2 sessions next week, you need to type into the chat, I don't want to have 2 sessions next week. Because otherwise I'm just going to stick with trying to fit in 2 sessions per week for us guys, because we're grade 12s. On the other hand, if it's causing issues for you, you should let me know. If you're not comfortable typing it in, on the comments, you can always send me an email saying, hey, it's just too much, Ms. Spence. There's so much going on and whatever. I'm totally fine. Just let me know. Anyone issues with having 2 meetings next week? So to reiterate, yes, 2 meetings next week. There will be one Monday at 9:30, and there will be one Wednesday at 9:30.